Hi, hello, good evening, one and all. Welcome to the session. Welcome to Gradeup. Can you confirm about audio and video, guys? If you are there, please let me know about this audio and video so that we can move on to the session. Hello, guys. So this mock test will help you in you know BARC definitely. So I've got here measurements. Actually, in this series, the first session I missed, that is questions on analog meters. So I took some questions from measurements, and I have taken some questions on networks. I have taken some questions on machines also, but I did not take up power systems question. So let me in this session. So I'll be taking analog meter questions on analog meters, or the electrical measurements part, and the power system, that too this transmission line and distribution line, transmission and distribution. Okay, I'm going to take up most repeated questions. I'm going to take up tomorrow, if possible. Tomorrow I'll try to make one more mock test that consists of networks and machines, and some other part, otherwise machines and power systems, load flow studies, fault analysis, the remaining topics I'll try. Okay, so let's move on. Hi Shankar, hi. Hi. Hi, everybody. So before moving on to the session, there's a small introduction about myself. My name is Naveen. I have around 7+ years of experience in teaching. Most of the times I'll be teaching networks, measurements, machines, and power systems. And this is my Telegram channel where you can join in and can download the study materials of these mentioned subjects. And even uploaded EDC study material also by Boylsted. You can download them, go to search and go to files and type the author name or otherwise the book name. You'll get it, I think. Right. And you can post your questions also, doubts also, so that I can try to solve. But please tag me. Please try to tag me. I'll definitely give a response. These are the Gradeup Super Platform courses, those who are preparing for GATE 2022 and 2023. The course is available in English and Hindi also. Right. The course structure and these are the number of live classes. These are the number of practice questions you are going to get. And I'm sure this will definitely help you in cracking the examination. Because if you are practicing 8,000 question, means that's not a joke. It will be definitely help you in cracking the examination. But the thing is, you need to digest the questions. You need to understand how actually they are asking. You can do that, then I'm sure. Even 8,000 also not needed. So let's check. It's completely depends on you. So let's move on to the session quickly and try to post your solutions in the comment box. Come on, my dear. Hi, Vandana and Krishma. Hi, how are you? How are you all? Look at this question. No eddy current and hysteresis loss occurs in. No eddy current and hysteresis loss occurs in. Can you tell me what could be the answer? So if you are expecting eddy current and hysteresis, means there should be a core. There should be an iron material. If there is an iron material or core material, that means what? Iron material. So the demagnetization process definitely leads to deviation, and it might lead to eddy current flow also in that iron piece. Okay, so PMMC, I have an aluminum former, and even we have iron piece also, right? So eddy current and you'll be having hysteresis loss also. Moving iron instrument, iron piece is there, definitely you'll be having. Electrostatic type, you have conducting plates here, conducting plates. So one plate is going to be fixed, another plate is going to be movable. So when the potential is going to be increased, definitely this movable plate is going to try to attract it towards a positive plate. You can move, you can make a positive plate also a movable plate, and negative plate as fixed plate, doesn't matter. Okay, so here we have conductors only, we do not have an iron piece. So you cannot expect any hysteresis and eddy current losses in electrostatic instrument. Now tell me about this electrodynamometer type instrument. Can you tell me about electrodynamometer type instrument? Is asking about no eddy current and hysteresis losses. Come on, my dear. Can you tell me about electrodynamometer type instrument? In electrodynamometer type instrument, you will be having a coil that is a fixed coil. So this fixed coil is connected like this, 50% here, 50% here. And in between the fixed coil, I'll be having a moving coil, right? So I'll be having a moving coil. So the moving coil connection, you can generally connect in parallel with respect to fixed coil. We call this fixed coil as current coil, by the way, and we call moving coil as pressure coil, right? Now, did you find any iron piece here? Did you find any iron piece here? Actually, you do not have an iron piece even in the electrodynamometer type instrument also. Even I have that also. You can find out if it is visible. Let me show you. Let me show you. I have some meters with me. Okay. So if you can see this one, this is your one fixed coil, and this is your one more fixed coil. There is your one more fixed coil. So in between the fixed coils, you can see the movable. So you can see the movable coil also. There is no iron piece at all. There is no iron piece at all. There is a supporting structures with a plastic material, but you do not have any iron piece in this instrument. Whether on mobile body or a fixed body, you do not have an iron piece at all. Okay, so definitely there is no chance of getting hysteresis and eddy current losses even in the electrodynamometer type instrument. Okay, I do not have an electrostatic instrument, so I cannot show you that. Okay, so this is also going to be the correct answer. When you have two options, I know it's very tough to select, but my intention is to say that electrostatic instruments and electrodynamometer type instruments does not have eddy current damping. Sorry, I'm so sorry, eddy current loss and hysteresis loss. Even you can go ahead with the electrodynamometer also. That is the reason why I've got that one. Yeah, in that one also you cannot find any iron. Look into this question. In a gravity controlled instrument, the deflection angle is proportional to. In a gravity controlled instrument, the deflection angle is proportional to. Is it proportional to measurement? Is it proportional to square of the measurement? It is proportional to sine inverse of the measurand actually, measurand and sine of the measurand. So it's a gravity control. I have a pointer. On the pointer, we'll be placing a control weight, right? We'll be placing a control weight. You'll be having a balanced weight here. When the pointer moves from here to here, like this, so your control weight also will be perpendicular, right? So this weight is going to pull the pointer in the downward direction. So this component is going to give you the control torque. So this component is what? If this is a weight, this component is opposite component is sine component. So your control torque is proportional to weight and is a function of sine. So the D is asking deflection. So deflection theta will be sine inverse of the measured quantity. Sine when you equate TC and TD, TD you can take up any I or otherwise V proportional to I. You can take up TD proportional to I or V. TC is going to be theta and sine inverse of I. So sine inverse of measured quantity you are going to get, right? Yeah, measurand means the quantity which actually we are going to give. That's it. Very good, Karishma. Right. Look into this question. Look into this question. Which of the following decides the time response of the indicating instrument? So I have a scale. Right? Maybe 0 to 10 amperes like that, and this meter is applied with some 5 amperes. Okay, so this is my 5 amperes location. Now my pointer, the moment whenever you give the supply, that supply is going to drive the current, and due to that current effect, you will be getting magnetic field. If it is a PMMC, there will be interaction between, let it be any meter, there will be interaction between two flux lines, and there is a chance of production of torque. electromagnetic torque. And the torque definitely tries to move the pointer from one place to another place, right? So I have my 5 amperes. So my pointer has to move from here to here. The pointer will never stop at 5. The pointer will go beyond 5 also. The moment when you give, because of moment of inertia, it may exceed the value of 5 also, right? And later slowly it comes back because of controlled spring action, and it will oscillate around 5 for a few seconds, not even 1 second, 2 seconds also. If it is properly damped, then it will settle near to the 5. If you draw a graph, it looks like this. This is my 5 amperes. Okay, this is my 5 amperes. Now, my pointer is going to move from 0 and it reaches more than 5, less than 5, more than 5, less than 5, more than 5, less than 5, like this. Goes more than 5, less than 5. You can take it as 5.2, 4.8, 5.1, 4.9, 5, and so on. It will oscillate like that. So until unless the pointer is getting stable condition, you cannot take up the readings. Okay. So this response, in order to get steady state response, this much of time you need to wait. This is called settling time, right? So this settling time can be reduced. You can reduce the settling time, the pointer settling time, by increasing the damping. So damping force is going to play major role in getting the reading. If you can damp the oscillations very quickly, probably within a short time you are going to get. Within this much of time you are going to get. So damping mechanism is going to play a major role in getting the stable value. Is that clear, my dear? Subhob, Karishma and Shivabala. Look into this question. I have T is equals to K into I. Deflection torque is equal to K into I is a torque equation of what? The torque equation of what? If you see a PMMC instrument, the torque equation is generally flux density, current flowing through conductor, area of cross section of the conductor, and number of turns on the coil. If you see the moving iron, the deflection torque is proportional to half or maybe equals to half I square into dl by d theta. So this is how for electro EMMC also you'll be getting I square into dm by d theta like that. So torque is proportional to just I only, not square of the current. So definitely moving iron instrument is not going to be the answer. And this rectified time instruments is going to be a RMS indicating meter anyhow. Look into this one. So which option is going to be the correct answer? The question is here. The deflection torque is in terms of, this is meter constants. Okay. So the deflection torque is in terms of meter constant for DR-Snowell galvanometer or tangent galvanometer, not for PMMC. PMMC, you can make this as you cannot make this as of course G will represent with B into A into N into I. So here also constant only, you can make it with G, galvanometer constant. Okay, but if they specifically mention like this K into I, you should go with the DR-Snowell instrument, because DR-Snowell instrument does not have a pointer. It will be having a mirror. On the mirror you have to project the light. So whenever there is a deflection torque, the light beam will be reflected, and that reflection or otherwise movement of light beam is going to be your deflection. So it is measured in terms of meter constant. We do not take the help of flux density, area of cross section of the coil. Of course, meter constant you will take up. Of course, it involves all those things. So this is meter constant. Okay, so be careful with this kind of question. Look into this question. I have so simple question. Let's finish within 40 minutes or 45 minutes odd, because I'll try to make one more mock test tomorrow, so that it will be less time. If I take up, then it will be better, I think so. If I go ahead more than 1 hour, I think it will be very lengthy session. Let's make it. Look into this question. The torque of electrodynamometer instrument is given by electrodynamometer. Electrodynamometer is nothing but electromagnet moving coil, right? Moving coil is brought from PMMC. Electromagnet is brought from MI, right? This is from PMMC. So PMMC and MI combination is EMMC, right? So generally your PMMC deflection torque is B into I into N into A, right? So we do not have a permanent magnet in the electrodynamometer type instrument. We have an electromagnet. So this permanent magnetic field is replaced with electromagnetic field, that is electromagnet field IF. We call it as fixed coil current, and this is going to be moving coil current. And this is going to be it is going to be replaced with mutual inductance dm by d theta. So TD is proportional to fixed coil current and moving coil current and the dm by d theta. So I1, I2 is nothing but fixed coil current and moving coil current. Okay, so A is the correct answer. Not exactly Karishma. D is not the correct answer. It is not. He is not asking MI instrument. MI instrument depends upon DL by d theta. Okay. But EMMC depends upon mutual inductance, because your construction is going to be like this, right? Half of the electromagnet here, half of the electromagnet here. Just now we have drawn one coil here, one coil here. Between that one coil, you will be having one more coil, that is moving coil. Look into this one. The deflection expression theta is directly proportional to V square into dc by d theta, corresponds to the capacitance of the meter is changing with respect to deflection. What is that meter? It's electrostatic meter or electrostatic voltmeter or not. So I have one conductor here. I have one more conductor here. Make one conductor as fixed and make one conductor as movable. You go ahead with the spring control. It's better. You can go ahead with the spring control, right? Now, whenever I give the supply, maybe 1000 volts or otherwise something, a large voltage. But generally, we take the electrostatic voltmeter to measure large voltages, because small voltage, if you apply small voltage, pulling the conductor towards the positive plate is somewhat difficult, because this will be having some inertia, right? And ऊपर से ये spring भी खींच रहा है, तो a small voltage, small potential difference will never try to attract the movable plate. You apply large potential, so whenever the potential is going to be formed here, so because of large potential, definitely this plate is going to move from one place to another place. So when the distance is going to be changes, the dielectric medium is going to be changes. Distance changes means you place a pointer on this one, your pointer will oscillate, right? So if the movable plate is going to change, the distance between the fixed plate and movable plate, dielectric medium is going to be changed. If the dielectric medium changes, capacitance effect is going to be changes. So capacitance is going to change with respect to deflection. By the way, the same expression for electrostatic voltmeter is same as MI instrument. TD is proportional to V square into DC by d theta. It is of electrostatic type. Okay. Very good, Karishma and Shivapala. Look into this one. A moving coil instrument gives full scale deflection for 1 milliampere and has a resistance of 5 ohms. If a resistance of 0.55 ohms is connected in parallel to the instrument, what is the maximum value of the current it can measure? So no doubt is connecting in parallel, so definitely it is going to be a ammeter, because if I have a meter, is saying that moving coil. So most of the moving coil, if it is mentioned, that is going to be PMMC type. So I have RM, I have a pointer. Now what I am doing is I am connecting a shunt here. If I connect a shunt, then it will be converted into moving coil ammeter. He has given meter resistance, that is 5 ohms. He has given shunt resistance also, that is 0.55 ohms. Shunt resistance will be obviously less than 1 ohm. Meter current is 1 milliampere, and what he's saying, what will be the, if I place this much of shunt, what will be the maximum value of current that can be measured? So extended current is asking. I know shunt formula. RSH is equals to RM by M minus 1, right? Okay. What is M? Multiplication factor, what is that? What is that? Extended current by meter current. Okay. So I is to be calculated and IM is 1 milliampere. Minus 1. is equals to Rm is 5 ohms, RSH is 0.55 ohms. So I into milli, if it goes up kilo, so is equal to 5 divided by 0.55 plus 1. 5 divided by 0.55, it will be leading to around more than 10. So 10 plus 1 approximately 11, 11 point something. So 11, if this kilo comes here right side, then it will be divisible obviously. 11 milli like that. So 11 milli, 10 milli in that range. SR. So use this, please solve, try to solve this one. Be careful, do not forget this kilo. Okay, so definitely if this kilo comes here, division na, yes, into 10 to the power of 3. 10 milli, yeah, yeah, maybe 11, 10 milli in that range. Look into this question. What is the series resistance required to extend 0 to 100 volts range of 20 kilo ohm per volt meter to 0 to 1000 volts? Okay, I have a voltmeter already, which is of 0 to 100 volts range, and that voltmeter sensitivity is around 20 kilo ohm per volt. Already that is the sensitivity. Now he wants to change the range of that meter to 1000 volts. Now what is asking? What is the series resistance you need to place? Already I have a voltmeter. Already it is extended to maybe extended or it can measure up to 100. So let me represent that Rm, and this is going to be RSC. So this can measure up to 100 volts. Okay. So this voltage range with a sensitivity of how much? 20 kilo ohm per volt. If you know the sensitivity, can't you calculate the resistance of the meter? So sensitivity is equals to RV by V. So voltmeter resistance is going to be sensitivity into full scale deflection voltage. Sensitivity 20 kilo ohm per volt and voltage is 100 volts. So volts gets cancelled. So 20 into 100 it becomes 2000. So it will be 2 mega. So this Rm plus RSC together it is going to be 2 mega. It is going to be together it is going to be 2 mega. Now this meter has to be converted into 1000 volts range. So already I have a voltmeter resistance of 2 mega, right? So it can measure up to 100. Now add some more resistance, such that it has to measure 1000 volts. It has to measure 1000 volts. So now what is this series resistance is asking. What will be the series resistance? Series resistance will be Rm by M minus 1. You can do that. Okay. Meter voltage you know, meter extended voltage also you know, but meter resistance. You can take up this 2 mega as meter resistance now. Okay. If you can treat like that, then you can do that one. So 2 mega Rm into M minus 1, that is V by Vm, that is V is 1000 divided by Vm is 100 minus 1. So it comes out to be 10 minus 1 is 9, 9 to the 18, 18 mega ohms. You have to treat this as now meter resistance in the same manner. So 18 mega is the correct answer. Very good, superb, Karishma and others. Look into this one. I have power systems questions now. The most appropriate way of mitigating the problem of interference between the power line and communication line. So when you have a straight lines and there will be a communication line also, So because of electric field, there is a chance of noise generation, and therefore you will not get a clear audio or clear signal. Communication is going to be disturbed. Communication frequency is going to be disturbed, right? Because of electric field linkages or flux linkages with respect to communication lines. So how do you avoid this one? We call this as interference as crosstalk. The transmission line is going to talking with communication line. Communication line is going to talk with transmission line, crosstalk. So this, if you wanted to avoid, you have to, uh, you have to shift the space or shift the place of this transmission line. After some distance, you have to go like this. You have to go like this. What is this? This is jump. This is called transposition, right? Transpose the power line, right? Very good, Shiva. Ah. Stringing chart is useful. Stringing or stringing. String means like this. Okay. It's a group of insulator connected. It's like a forming a rod. Okay, string. So this string will help you to hold the power conductor. The string will help you to hold the power conductor. Now this stringing chart is going to help you. So I have one more string here, and if you connect the power conductor from here to here, what this stringing chart is going to help you? This stringing chart will help you the sag and tension of the transmission line. Sag and tension of the transmission line. It will help you to find out the sag and tension with respect to temperature also. You can take up. Okay. C is going to be the correct answer, right? Can you tell me about this one? I have got very simple questions because these are most repeated questions in some kind of examinations. Look into this one and tell me. The self GMD method is used to evaluate self GMD or otherwise geometrical mean radius. Anything is both are same geometrical mean radius. So I have a power conductor, but because of electric field and the ionization of air around the power conductor, so the effective radius of the conductor is going to be changes, and it leads to change in inductance of the conductor. So much influencing factor is going to be influence. Much influencing factor is going to be inductance of the transmission line. Inductance of the transmission line. So self GMD analysis, just GMR analysis is going to evaluate the inductance of the transmission line. Now tell me, I have transmission line here. Now I have one more transmission line here. Okay. So this radius is also going to be effective radius also going to be changes. Now can't you expect the capacitance between this one? Now can't you expect the capacitance is going to be affected? Capacitance is going to be affected. Will it going to affect the capacitance or not? You think about this one. When the transmission lines are like this, equi-spaced or otherwise not equi-spaced actually in a straight manner, like this, definitely it is going to affect the capacitance also. And when the transmission lines are equilateral triangle manner, now here also effective radius is going to be changes. Now, can't it going to affect the capacitance or not? Think. The first priority will give it for inductance. Now, will you give the second priority for capacitance or not? No, I am not from IIT Madras. I am from JNTU Hyderabad. Ananya, look into this one. The surge impedance of 400 kilometer long overhead transmission line is 400 ohms. For a 200 kilometer length of the same line, the surge impedance will be. Generally, how do we calculate surge impedance under root of inductance per kilometer divided by capacitance per kilometer or not? So length of the transmission line, whether it is 200 or 100 or 500, doesn't matter. So it's taken with respect to kilometer per kilometer. That's it. Inductance by capacitance, inductance of the transmission line and capacitance of the transmission. So generally, don't make it as zero. Don't make it as zero. And don't ask me what is the surge impedance. Okay. So line should be there first of all. If line is not there, how do you define surge impedance? Okay. Don't make it zero. 200. Don't make it zero. Okay. So the 200 and 400 doesn't make much difference in the surge impedance loading. Sorry, surge impedance value. Is it going to be 400 or 200? Now look at this one. A surge voltage of 1000 kilovolts is applied to an overhead line with its receiving end open. Receiving end is open. So if the surge impedance of the line is 500, then the total surge power. Surge power generally surge impedance loading. What is that? V square by ZL or not? ZL or otherwise characteristic impedance loading. Characteristic impedance. So how much is the operating voltage? The operating voltage is going to be 1000 kV. So 1000 kV whole square. So 1000 whole square that becomes 1 mega. Kilo square it will become mega. Right? It will be very large value. So you can write, let me take up it as kilo square will be mega, 1000 into 1000. So 1 mega, already mega is there. Divided by ZC, characteristic impedance 500. Okay. So 5 to the 10, 2000 mega. Is it 2000 mega or 2 mega? 2000 mega, no? Look into this question. I'm hiding myself so that you can answer it. Voltage control. Match the items in list 1 with items in list 2 and select the correct answer using the codes below. Improve the power factor. Which is going to improve the power factor? Generally, definitely, there should be a capacitor. If there is a capacitor, definitely it will improve the power factor, right? Okay. Definitely, if there is a capacitor, definitely it is going to improve the capacitor, improve the power factor. But the thing is, whether the capacitor should be in parallel or series is a question. So definitely, capacitor power factor improvement is going to be done with a capacitor. Now the capacitor should be in parallel or series is a question. So it should be shunt. It should be shunt. Correct in parallel. A2. Reduce the current ripples. If you want to remove the ripples, we'll be placing inductor. We'll be placing inductor because inductor is not going to allow the sudden changes in current. So ripples are going to be removed. Similarly, if you want to remove the voltage ripples, capacitor, you place capacitor. So reduce the current ripples will be reactor. You should connect in series. So 2, 4. Increase the power flow in the transmission lines. If you want to increase the power flow, you have to compensate the reactance nature of the transmission line. How do you compensate the reactance of the transmission line? By placing the capacitor in series. So that is why series capacitor is also called as power system stability device. Series capacitor is also called as stability device. Reduce the Faraday effect. Receiving an voltage is going to be greater than sending an voltage. So how do you do that one? So if voltage increases, if you want to maintain or reduce the voltage, try to connect at the receiving end, try to connect a reactor. So it is going to consume the reactive power. Inductor is going to consume the reactive power. Because of consumption of reactive power, this bus voltage is going to be reduces. So I can take up it as reduce the Faraday effect. You can take up this as 1. So 2, 4, 3, 1. B is going to be the correct answer, it seems. Very good. Thank you, Karishma and Shivapala. Look into this one. The main limitation for power handling capability of the short length transmission line. The length of the transmission lines are very less. Short transmission line and cables. Cables also going to be, we are not going to place for long lines. It's also going to be short distance. It's not more than even 60 kilometers, 80 kilometers. Okay. We do not go for that much also. Okay. So cables. So short transmission line cables will be limited by temperature, thermal effect, temperature limit. Okay. Thermal limit is going to influence the power transfer capabilities. Medium transmission line is going to is influenced by voltage. Okay. So he's asking anyhow thermal limit. Oh, sorry, short transmission line, short length transmission line. So it's a thermal limit. So medium transmission line limitation is going to be operating voltage, and long transmission line is going to be limit is stability, power system stability. If the line length is very large, if there is a sudden short or sudden open circuit false, if there is an open circuit of transmission line or short circuit of transmission line, that is going to lead to a lot of change in power, So definitely it is going to undergo acceleration or deceleration of the rotor in the synchronous machine. So definitely stability, because when the synchronous machine is going to be under swinging, then the power delivered by the synchronous machine will not be under constant frequency. If the power transferred by the synchronous machine is not under constant frequency, we cannot take up, that power is not going to be, I can call it as, disturbed power. About leakage reactance, the moment when you look at leakage reactance, you'll get, I think, leakage reactance is inversely proportional to length. So 50 kilometers length is there, long cable is having 1 mega, and 100 kilometers So RL2 will divided by RL1 is equals to L1 divided by L2. So resistance I need to calculate insulation resistance or leakage resistance. Okay, fine. L1 is 50, L2 is going to be 100 kilo. RL1 is 1 mega. So it will be half of or not? Because length is doubled, resistance is going to be half. 0.666. Huh? So there is no option. The better one is going to 0.66 is also, if it is none is there, go ahead with none, better. Yeah, 0.66 again, mega, it will definitely difference. 5,000 kilo, 6,600 kilo, large difference is there. Look into this one. Surge impedance of a 50 miles long underground cable is 50. Just now we have seen. Surge impedance is not going to be influenced by the very much length or length. Okay. So it is going to be same whether it is 25 miles or 100 miles, you are going to get same. Ah. Good effect of corona on overhead lines is good effect of corona on overhead lines is two. Corona means what? I have a power conductor. So what is going to happen? Definitely, the air around the conductor or air around the surface of the conductor is going to be ionized. Is going to be ionized. So if this is going to be ionized, then there is a chance of formation of a bluish layer. You can expect there is a chance of formation of a layer. Maybe you can expect like this ionization of air. Right. So when a surge is attacking the transmission line, maybe a thunder or otherwise any surge is attacking the transmission line, right? Voltage in the form of voltage. The impressed voltage on the power conductor without corona is going to be more. The impressed or pressure on the power conductor is going to be more. With corona, this corona or this imaginary layer, or you can see also bluish layer if the voltage level is going to be increases or if the air is going to be ionizes. This layer is going to act like a safety thing. It's a protecting the power conductor from the surges because the surge has to attack this layer, then it has to attack the conductor. So the impact of surge on the conductor is going to be decreased. Without layer, without this bluish layer, you can have more effect. With bluish layer, you can have less effect. So it is acting like a protecting cover. So that is a good effect. The rest is going to be power loss and all those things. Bad effects are there. Uh, what is a good effect? Is this surge impact on the power transmission line is going to be reduces. Ananya, can you tell me? Can you post your question once again? I missed your question. You asked some question about are you from IIT Madras? I am not from IIT Madras. I am from JNU Hyderabad. I said that is a question I have saw. I have seen. Look into this one. Ring mate distribution is preferred over radial distribution. Go ahead with the radial distribution. If I connect the feeder here, okay. Now my loads are going to be here, 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 and here. So as you move on from this side to this side, and now you are going to get a voltage drop here, V1, V2, V3, V4. The voltage drop is going to be changes. So definitely the load at this end of the line or distributor, end of the distributor is going to get less voltage. V4 is going to be definitely um, less. That is the reason why in order to overcome the drawback of radial system, we will feed this radial distribution line with it at both ends. At both ends. Or otherwise, you can go ahead with the ring main system. So ring main system, the current will be gets divided, obviously. So you can minimize the voltage drops. You can minimize the voltage drops. If there is something breakdown here, if there is something breakdown here, then at least part of this load is going to be supplied on this side. Because you do not have a continuity here. At least part of the load is going to be supplied. Reliability is going to be more. If a breakdown is going to be happened here, completely it is going to look like an open circuit. Radial system is going to be look like an open circuit. So complete power loss or power shutdown is going to be there in radial system, right? In ring main system, you can avoid that. So reliability is more, power reliability is more, and voltage drop can be minimized. Okay, that's the thing. Voltage drop in the feeder is less, the supply is more reliable. First option. Very good, Karishma and 19th A. Everybody, Karishma and Shobala, thank you. Ananya is asking, no doubt, no problem at all. Uh, in engineering, I think these days they are keeping it as minimum 70% like that, 65%, 75%, 70% like that in few IITs. Some IITs also fixing more than 75. 10th and intermediate doesn't much influence the admission in the IIT. BTech is going to influence the BTech percentage or bachelor's percentage is going to influence the admission in the IITs. So that should be 65 at least, minimum 65 or 70 like that. Each and every IIT is going to be changes. Not going to influence 10th percentage CGPA, 12th percentage, very rare. The purpose of God ring is, so this is my cross arm, this is my tower, and this is my metal pin, and I'll be having a power conductor. By the way, you can have a disc here. Like this, you'll be having disc. Between each and every disc, the metal pin will be there. Okay, I'm not showing it. You cannot see that. The metal pin is there. The metal pin is not going to be continuous. Okay, if I have a disc like this, so pin will be here and pin will be here. Like this. Like this. So porcelain material, you'll be having like this. So here is my power conductor. What should I do? So because of this metal pin and the voltage establishment across these insulators, generally voltage establishment or voltage distribution across the insulators will be changes because of this shunt capacitance effect. Between this tower body, tower or between the ground, you can say, because this tower foot is connected to ground, no. So metal pin to ground, there is a chance of existence of capacitance, so shunt capacitance. So which leads to unequal distribution across the string or across the insulator disk. Okay. So the insulator disk which is very near to power conductor is going to experience more voltage, and the insulator which is far away from the power conductor is going to experience less voltage. If it is experiencing more voltage, generally each and every disk is going to withstand only 11 kV. If it is experiencing more voltage, then there is a chance of puncture or failure of that disk. So in order to avoid this unequal voltage distribution, what we have to do is, maybe you can take up it as V1, V2 and V3 all should be equal, uniform voltage distribution you need to get. So that can be done by increasing the cross arm length, and you can go ahead, you can increasing the cross arm length and you can design the insulator disc properly. That is what grading of the disc. And the third option is most practical option is going to be uh, like this. You place a guard ring. So this will forms one more capacitance like this. So this capacitance will inject the charging currents, and definitely it leads to so this charging current must be equals to the current flowing through this shunt capacitance effect. So and therefore you will be, end of the day, you'll be getting this one, uniform voltage distribution. Which there's all these things, increasing the cross arm, designing the insulator disc with uniform uh, properties or uniform manner, having a guard ring, all these to increase the string efficiency. Okay, so it will not reduce the transmission losses. It's not going to show the impact on uh, transmission line. It's going to show the impact on distribution of voltage across each and every string, each and every disk. Reduce the earth capacitance of the lowest end? No, it's not going to be like that. So increase the earth capacitance? No. Is the main purpose is to have a uniform voltage distribution. So none of these are correct answer. Ah. Krishma, how can you tell me, how can you say that the lowest reduce the earth capacitance of lowest unit? Lowest unit is this one. How do you affect that? No, it is not only going to do this one. We are going to make uniform voltage distribution. Capacitance effect is you cannot make down, you cannot make increase. Opposite, another capacitance effect is going to be formed. There is a chance of injection of currents from this side. So there is a chance of uniform voltage distribution. That is what I am saying. So how can you expect earth capacitance? So this capacitance to the metal pin, how are you expecting this is going to be low? How are you expecting capacitance sigma A by D? Are you changing distance? Are you changing the area of cross section? Are you changing the permittivity of this free space? Huh? I'm going to place this guard ring, which is going to create an extra other side capacitor, which is going to inject the charging currents. And we should make that this charging current and this charging current are going to be same so as to make voltage as uniform. Lowest, it is not much going to influence the capacitance. No, they do not ask you any problems in the placements. Highly impossible. Very rare they'll ask you in the placements. Ohm's law. These are the faculty members on Gradeup Super platform, and these are the super subscribers which have got rank. Those who have got the ranks in Gate 2021. And this is my Telegram channel. You can join in. You can post your questions and doubts if you have any doubts. So that's all for the day. To maybe possibly I'll try to make a session tomorrow so that I'll get some questions on machines and remaining power system. Okay. All right. So thank you so much. Have a nice day. Bye bye. See you.